So I think we can start. So welcome everybody. Today I'm very pleased to introduce Angela. She was an undergraduate student in Pucki Hill, and she got a PhD degree from MIT. Nowadays, she's at the University of Chicago, where she's the Dean of the Division of the Physical Science and the Albert A. Mission Distinguished Service Professor of Astronomy and Astrophysics. Her research includes astroparticle physics and cosmology. In particular, her work has focused on the highest energy cosmic haze, indirect signatures of particle dark matter, cosmological effects of magnetic fields, natural inflation, and the internal structure of neutron stars. For her many achievements, she is the recipient of several honors and awards. Recently, she became member of the American Academy of Arts and Science. Today, the title of her talk is Space Observatories for Ultra-High Energy Astroparticles. So thank you so much, Angela, for accepting our invitation. And please, when you are ready, you can start.
Thank you so much, Thiago. It's lovely to be able to share some of our work with you. I'm sorry I can't not be there in 3 dimensions because I'm told that was beautiful and I haven't visited yet. So I hope I get a credit for a future visit. Anyway, but
Yeah.
at least I can go there and come back faster in 2 dimensions, but I know I wouldn't enjoy as much as if I were there in real life, in 3D, that's what I mean. So it's a pleasure to be here, and I want to share with you what we've been working on. These are space observatories that we've been building and designing. The Space One Poema is the goal of this effort, and we designed it with NASA funding, a conceptual design, and now it is in the Astro 2020 prioritization plan in the US, but it is an international collaboration of 13 countries. And so we put together this design for Poema, and the name Poema, I chose the acronym, so it spells out poem in Portuguese, but with 2 M's. And I'll introduce those names in a little bit later, but let me just say it, and then it will show up in writing in case you didn't pick it up. So Poema stands for the Probe of Extreme Multi-Messenger Astrophysics. And that's the spelling for that. For the other acronym, USO, it's Extreme Universe Space Observatory. And this is a longer, USO is leading into Poema, and USO is a 20-year effort in which many different types of payloads, both in the ground and in balloon payloads, and one in space right now inside the International Space Station, have been developed to be able to study the highest energy cosmic rays and neutrinos. And we launched USO SPB1, and we are now building SPB2 to launch in 2023. SPB is a NASA acronym for super pressure balloon, and USO SPB is the payload that we are building to put on these balloons. So, but let's start with the science. The science that we're trying to do is to answer a couple of very important questions in the field that we call astroparticle physics. So when I was in my PhDs at MIT, I was studying particle physics theory, and astrophysics came in during my thesis on strange stars. And that I discovered a whole world of effort, nascent effort at the time, this is late 80s, trying to use the universe as a particle physics laboratory. And we're still doing that. Questions like the dark matter of the universe, the dark energy, are very much particle physics and astrophysics. In the case of what I'm focusing on today and the projects that I'm talking about, it is about the highest energy particles, which are much higher energy than we can do in laboratories. However, we can't control the beam line. So, compared to LHC, we can't do precise measurements, but we can do very good measurements that give us a sense of what's happening. And what do I mean by ultra high energy cosmic rays, which is one of the topics for these projects? We want to find out what the sources of these ultra high energy cosmic rays are, what their composition is, where they're coming from, and what can we learn from them in terms of particle interaction. So the plan to answer that question is to measure the spectrum, the composition, and the anisotropies of cosmic rays of energies above 10 eV. An eV is a 10 to the 18 electron volts if you haven't run into them before. And so the projects we are designing is to answer above 10 to the 19 electron volts. Today, we have lots of other measurements that are pretty precise up to that energy. And then we're trying to extend for the next couple of orders of magnitude. In terms of the other question that we're also trying to explore with the POEMA payload is the sources of the astrophysical neutrinos. Neutrinos are wonderful particles to use to do astrophysics and to also understand physics interactions. They are very difficult to detect, but when you do get to detect them, then you can learn about things that are pointing in the direction they arrive. You also learn about flavor of oscillations, all kinds of interesting particle physics. And we have used some to do particle physics. We've used the neutrinos from the sun, neutrinos from supernovae, and we're now starting to open the window into neutrinos that are accelerated in astrophysical sources at very large distances, for example, black holes. And blazars is one of the correlations that IceCube has reported. So what we want to do to try to understand what these astrophysical neutrinos are, where are they coming from, what are the sources, and how do they get accelerated to the very high energies, what we will be contributing to that question is a multi-messenger coincidence between gamma rays, gravitational waves, and neutrinos. And in the case of POEMA and ISO-SPB, is neutrinos above 10 to the 16 electron volts, so above 10 PeV. We want to answer those two questions, and at the same time explore other questions that are related, which is, when we look at particle physics and astrophysics with energies much larger than the ones in accelerators, maybe we can find some relics from the beginning of the universe. Maybe we explore supermassive dark matter, extra dimensions, and so forth by looking at the interactions. So just to set up, I gave you a summary of where we're going, but let me start with a lower level of introduction here. So as everybody knows well, the sort of majority of what we know about the universe comes from the electromagnetic spectrum. So in other words, by photons that bring in information about everything that's happening out there that we know of. Now we know there are more things that we can see because we can see other things than electromagnetic radiation. But we have, explored starting in the mid of last century very well the whole range of different emissions that we see, for example, all the way from radio waves to gamma rays. The sort of leading way of doing observations is still in the visible range, but that's a very narrow range. We have a lot of infrared capabilities too to try to see how the universe evolved as you go closer to the Big Bang. But a lot is known by having many multi-wavelength observations of different, and here I just give two examples. In the radio extreme, the ALMA Observatory in the Atacama Desert is doing a brilliant job in understanding the millimeter and submillimeter range. And then Fermi is another example, Fermi Gamma Ray Telescope in the gamma ray range. So between those two, there's a lot of other telescopes and also telescopes further in scale for the radio side and further in scale for the gamma ray detection too. When you add other multi-messengers, other messengers to the story, the first messenger that comes up is cosmic rays. And cosmic rays we know since 1912. And in 1912, we have Victor Hess establishing that the ionizing radiation that was was a puzzle at the time, was not coming from the ground, but was coming from outside of the atmosphere. And he did that by taking some ionizing radiation detectors up in a balloon. So we are still using balloon to understand cosmic rays. And he started the field back in 1912, also with a balloon. He went up himself. We now send the balloons without us. We have computers that do the job. But he went up all the way to 5 kilometers to show that the flux of cosmic rays increases significantly as you go up in the atmosphere, meaning that the atmosphere is protecting us from a flux that's coming from outside, which is cosmic, not made by the Earth. That's the origin of cosmic rays, the beginning of it. And now we have a huge range of cosmic ray energy. which basically doubles the energy range for astrophysics. So, when people think of cosmic rays, sometimes they think, oh, there's one type of cosmic rays. And it's really as broad a spectrum of cosmic rays as is the electromagnetic spectrum. So we have, all the way from low energy cosmic rays to very high energy cosmic rays to ultra high energy cosmic rays. Gamma rays have also been expanding over the last decades, the detection of energy range going higher and higher with techniques similar to the ones we observe cosmic rays. And neutrinos, we're still hoping that, to see the very high energy ones, but we're starting to see the astrophysical ones. So the range on the neutrinos is also expanding. If we do just, to be energy, and if you go then to, wavelengths, low neutron star collisions have been, coalescence has LISA or ELISA will be even exploring even longer wavelengths, and then pulsar timing arrays are the biggest wavelength, the largest wavelength that we're using to understand the universe. Decades ago, so previous century multi-messenger, this century previous century multi-wavelength. Now we call these things multi-messengers because going down like a power law e to the minus 2.7. Extragalactic cosmic rays, which we know should be starting at some point. We know it has to be, around below or equal to 8 eV, but we don't know exactly what that transition is, which is why I put the colors sort of overlapping. To detect, as I mentioned, all these different things, you need very different detectors. And in the low energy, high flux region, we can put things in space and detect the primary cosmic ray particle directly. And then when we go to very high energies, we can't do that because the fluxes are very, very low. You would need a humongous detector in space, and that's expensive. And, even then it would be very difficult because, the flux is 0.1 per kilometer square per century when you get to 10 to the 20. So this is not easy to detect with direct detection of the primary. But fortunately, as we learned from Victor Hess, the atmosphere is protecting us from the cosmic rays with very high energies, and is actually making a translation that we can observe. And that finding dates back to Pierre Roget, who back in 1937 already estimated that cosmic ray primaries, the particle that arrives on the top of the atmosphere, can reach at least 10 to the 15. And he did that by just placing different detectors of cosmic rays on the ground with a distance and noticing that they get hit together from time to time. And that together hit means that one primary generated a whole shower of secondary cosmic ray particles or secondary particles. And that's what he's detecting from time to time. He also led the construction of CERN. So here's one simulation of a proton. And on the top left-hand side, we're following the particle production as the primary center of mass or center of momentum frame. And you can see the production of different particles growing and then reaching a maximum and then decreasing. This is for a proton of 10 to the 14 electron volts. We're talking about 10 to the 20, so a lot more particles, but this gives you a sense of the way that both the number of particles are being developed as a function of altitude. And so that's the pink curve going to a maximum and then decaying. And this is the number of charged particles and the height if it's coming vertically. And then the other plot in the bottom left is showing the distribution of particles on the ground. It's dominated by the red, which are the electromagnetic cascade, as we call it. And that's electrons, positrons, and photons. Then we have the second group would be the muons in gray. We have also hadrons and neutrons. So these are some of the particle composition, and lots of neutrinos too. We don't see those, which is why they're not plotted here. So that's the story for a 10 to the 14. And you see the scale here is 1 kilometer, 1.2 kilometers for the decay of that pancake of particles coming on the ground. As you go to 10 to the 20, the distance from the core to the edge of the shower is a lot larger. And so to detect that, we have to put detectors at, we can put detectors at much further distances, as I'll be talking about soon. So how do we observe these cosmic ray, very energetic ones? So we have one way, which is to put, just like Pierre Roget was talking about, put a bunch of detectors on the ground and separate them by some distance, and then you will see from time to time the cosmic ray numbers showing up at the same time, electromagnetic and muon components. Or you can do something even more sort of elegant, which is to observe the two types of emissions that these showers make. In the forward direction, they make Cherenkov emission, and that is what, if you place a detector, a photodetector below the shower, then you would see this emission, and that's what's used to do gamma ray astronomy at very high energies. It's the technique that is used to observe the gamma rays, TeV energies and above. Then we have another wonderful thing, which helps us at the 10 to the 20 electron volt energy. And the energy there is relevant because, the higher the energy, the further you can see these things. And also the higher the energy, the flux is lower. So the fluorescence technique is something really wonderful that can be used. And so this technique is the following. A shower, such as the artist impression here on the plot, will have this electromagnetic cascade that basically excites the nitrogen in the atmosphere, which fluoresces. And so by observing the fluorescence of nitrogen, it will look like a light bulb in the ultraviolet moving at the speed of light in the atmosphere. One can see a shower of 10 to the 20 sitting, tens and 100 kilometers away from the shower itself. So that really helps with these low fluxes. And so in translation, what we will do then is use the atmosphere as a whole as our detector, and we instrument in space missions with telescopes looking for this ultraviolet emission. So we could do two things in space. We can look at the ultraviolet emission of ultra-high energy cosmic rays, or we can look at the Cherenkov emission that's coming down on the shower. The problem with that technique is that you would have to place your telescope below the shower, which is not very convenient for ultra-high energy cosmic rays. But it's perfect for neutrinos, because neutrinos, they make showers on the upward going direction instead of the downward going direction. Neutrinos come through the other side of the Earth. Say a tau neutrino will come through the Earth, eventually has a probability of interacting and making a tau lepton. That tau lepton has a probability of decaying in some direction, and then you can see the shower created by that tau lepton. So that's how we're going to use both techniques to look at two types of particles in POEMA and SPB2. Now, what we know about ultra-high energy cosmic rays come from the telescope array and the Pierre Auger Observatory, and I was involved in the Pierre Auger Observatory from the beginning, and it is now at, I think, 18-country collaboration, but it used to be 19. The telescope array is a 5-country collaboration. It's based in Utah, USA, and telescope array is 700 kilometers square array, and it's now being, there's an increase on the area, so there's a growth to be able to match the Auger. So Auger is the leading observatory with 3,000 square kilometers of detectors in Mendoza, Argentina, and 4 fluorescence telescopes, and in the case of TA, there's 3 fluorescence telescopes. So what we mean by these two types of the array and the fluorescence telescope is 2 different techniques to look at the same showers. So let me show you Pierre Auger in a cartoon or a little video that was put together. And if you have that shower that's developing, it hits the ground, and in yellow are the detectors on the ground. So in the case of Auger, there's 1,660 of these detectors. These detectors are placed, the majority of them, 1,600 of them, with 1.5 kilometer distance from each other. And when the shower hits the ground, you see that the lighting up is the cartoon of saying, we have detected something above the background in these detectors at this time. And by trying to translate the yellow signal into a shower, we get an energy, we get a direction, and we get a composition, but not as great as if we can take the blue light in this image, which is supposed to depict the fluorescence emission of the shower. It should be blue rays coming from the shower to the telescope, not the other direction, but we didn't pay close attention when the video was being produced. I guess Superman X-ray vision was in the video designer's mind. But this emission in blue goes to the telescopes, and that's how we see the shower. But for the fluorescence technique to work, we need it to be dark. So that it can't be during the day, so it has to be during the night. And it has to be when the moon is not very bright. So because of that issue, it's a lot better for the statistics of the gathering of data in Auger to use the ground array. And for more precise measurement, having hybrid measurements of both the fluorescence and the ground is done 10% of the time when when it's night and the moon is out of the way. So, sorry, 10% duty cycle and the other is 100% duty cycle. Okay. So here is an image of the Auger detectors. So they are placed at 1.5 kilometers from each other. These are water Cherenkov tanks. And so when the particles from the shower or any cosmic rays cross the tank, you would then see some light with photomultiplier tubes that then are radioed into a station. These are self-sufficient. Let me show you first the actual distribution in red, so you can see further and further along that array. And here's just a picture of the younger me next to one of the detectors before it was deployed. And this is a water Cherenkov tank with a solar panel. This thing got actually, the box got redesigned because the cows love to scratch their backs. So it's actually a much more smooth version of the field, but this is how it was placed next to our campus there in Malargüe, Argentina. And then we have the 4 fluorescence telescopes that overlook the site. So you can see both the ground array signature and the fluorescence at the same time. All right, so here is a compilation of actual measurements as opposed to that, sort of compiled, put together one-liner for the cosmic ray flux. And this is the flux as a function of energy all the way to 10 to the 20. So you see that at the highest energies, the black, which is Auger, and the sort of greenish blue, which is a telescope array, those two are the only observatories at the energy range that we're talking about. And Poema is exactly to come in and help out at 10 to the 20, above 10 to the 19, but at 10 to the 20 in particular, where the statistics starts getting to be very difficult. To get better statistics at 10 to the 20, you need even bigger than 3,000 square kilometers. And that's where the idea of going to space and using a much bigger volume of the atmosphere comes in. And what you can see is that this is the flux of cosmic rays detected by many different types of observatories. But it's the flux multiplied by e to the 2.7. So the 2.7 was that average power law. And now that we took that power law away, you can see that, it's kind of flat to begin with. Then there's a knee. Then there might be a second knee. I think most folks are now convinced that there is, but that's pretty new. And then an ankle over here, and then a dive, right? So we come in at the ankle and the dive, and here is where we think extragalactic sources are going to be the most responsible for this flux. Below the ankle, somewhere, there's a transition between one and the other. And so all the energy, all the cosmic rays below the ankle are likely to be dominated by more close by sources, say within our galaxy. Now, the Auger, we just had a very big conference, the International Cosmic Ray Conference, or the Astroparticle Conference this past summer. So ICRC is the name of it in 2021. And here's the latest Auger spectrum. And it has preliminary in it because it hasn't been published, but it shows you the systematic errors in gray. And they go in a diagonal because now we're actually plotting the flux times e to the cube. And then it shows, the sort of second knee, ankle, and a little flatness, and then coming down. And, again, we're trying to explore the area where the fluxes are the smallest at 10 to the 20. Extragalactic is what I mentioned before, that we know it should be starting at least by this line, but is likely to have begun a little earlier. And the reason we're so confident is because Auger has been able to to detect something which, remember, cosmic rays are charged. That means that magnetic fields all over the place will make them arrive on Earth isotropically. So we don't point back to where they come from at low energies because they are turning around on their way from source to us. So it gets erased information where they came from. At the very highest energies, the turning around on the same fixed magnetic field will go down. But then comes in another problem, which is that maybe it's not all protons. So if we're changing the charge of the particle and at the same time making the energy higher, there is which charge are we talking about? Which component of the composition are we following? But the good news is that with enough data from Auger at 8 times 10 to the 19 electron volts, sorry, 8 times 10 to the 18 electrovolts, close to 10 to the 19, we start seeing a dipole. That dipole is not very strong, it's 6.5%. And that dipole, the news that gives us this extragalactic component sort of confirmation, we thought it was going to be extragalactic anyway for physics and source reasons, but this is a confirmation of that expectation. Is the fact that the dipole does not have any correlation with the galactic plane. It is pointing away from the galactic plane in a sort of direction that has something to do maybe with the supergalactic plane, which is a plane where galaxies are distributed around us. But certainly it does not seem to know that there is a galaxy. So these, above these energies, we are looking at extragalactic. So here are 3 plots of the same data: equatorial coordinates, galactic coordinates, supergalactic plane coordinates. And the dipole is in, the red is the more flux towards the red. And therefore, we don't see it pointing, for example, towards the center of the galaxy. Got it. So, it is extragalactic after this energy range. When do we start actually pointing to sources? When do we start seeing sources in the sky? There are hints that this should be happening around just when the sources become, when the flux gets lower and lower. And that's a challenge, because we want to look in the sky and say, it's coming from Centaurus A, or it's coming from NGC 253. The problem is that's exactly when the number of particles are getting to be lower and lower and lower. So, that's the reason to try to do a bigger exposure, a bigger volume, and a bigger number of particles per energy bin. But with those data, one can see some correlation. So the red is more flux again, and those hot spots do correlate with, for example, active galaxies like Cen or starburst galaxies like NGC 4945. So the fluffiness, or the lack of resolution on the direction of a hotspot keeps us from actually being able to determine what the source is, but we have some hints. And these are 2 of the possibilities: starburst galaxies or M80 or AGN, like M87. And so this is some of the possibilities, just showing you pictures of these active galaxies, either starburst, meaning a lot of star formation and a outflow from those galaxies, or a starburst or an AGN, an active galactic nuclei type situation, in which you can even image with the Event Horizon Telescope the accretion disk around the supermassive black hole of M87. So these are some of the possible sources, but the data is not enough to make sure that we know which source it is. And even maybe it is a correlation with the distribution of these galaxies and not necessarily coming from the black hole itself. So some open questions there, which would be helped by having a lot more data at the highest energies, which is what I'm repeating here. Basically saying that this range of energy is statistically limited. The fluxes are pretty low. We need to have a lot more volume of detector space to be able to point back to the sources and understand what's going on at that energy range. Then there's another question, which might have come up to you if you didn't see this before, is why is this flux turning around? So you might think that, these knees are transitions from, say, one element to another. An ankle may be a new source. So the ankle is, some source coming down and a new source coming up. And this would be, say, the extragalactic source taking over from the galactic source that is coming down in terms of flux. But then why does it turn around and come down again? So one obvious explanation is the same we used over here, which is that there might be a maximum energy of the sources, and we reach the maximum energy, and from then on it goes to close to 0. The other explanation, which was a sort of one reason to do this experiment to begin with, these experiments, is what's called the Gzk effect, and I will introduce it in a second. But let me explain the Emax option. So maximum energy, if these were only protons, it would be kind of surprising that the shape of the spectrum. But it turns out that when we look at the composition of what's happening at these very high energies, it's a lot more interesting story than just protons. So how do we know what a shower is like? There are 2 measurements that give us indirect measurement of the composition of the primary. One is the maximum of the shower, and this is the average X max as a function of energy. So let's take, and here's some lines. So let me explain the lines before I show you the data, which is also on the same plot. The lines say of hydrogen, helium, nitrogen, silicon, and iron. Say, let's take an iron nucleus at 10 to the 20. So that is 10 to the 20 energy of the whole nucleus, which means that energy per baryon you divide by 56. So the kind of maximum of that shower is similar, to if you divided that, if it were 56 protons. So 56 protons means divide by 56 and you end up in the same place. So the interaction of a given shower of a different species, right, is if you just separate the nucleons, then the iron at 20 is equivalent in terms of X max to the proton at much lower energies, about 56 lower. And that gives you a sense that this point here maps to that point there in iron, and the same thing for all the other ones. So that's how you can relate, one line to the other line on the maximum of the go to higher altitude. So this is the X max, so 800. Deeper, lower altitude, higher gram per centimeter squared. So I hope, let me repeat. So as you move in higher energy, the shower for a given species, let's just take a proton for now, goes into deeper in the atmosphere. So the cross section is smaller, the higher energies for a given proton. And then as you correct, if you take an energy here and you translate to iron, that's how you map these two sides, just by multiplying by 56 to make life, it's more complicated than that, but that gives you a sense of the story. So this is, lower altitudes where the peak goes, so it's more deeply penetrated. So that's how you can read this plot. And then this other plot is the fluctuations from shower to shower. So if you take, say, a proton shower, you have one proton and the probability of it interacting is whatever it is, and it might get lucky and not interact for a while, so it can interact deeper than its average interaction. For iron now we have 56 things with probability of interaction, so the probability of interacting roughly in the same place is higher, because 56 folks being lucky is less likely than one. So the fluctuations are smaller for iron versus proton. And that's what's plotted here in red, and in blue, dark blue would be below this plot. Okay, so anyway, now we know, what to expect. And then we go and measure these things. So you measure for a given energy. The energy is the integral under the shower. We measure what is the maximum shower depth. And so the deeper it comes in the atmosphere, the higher the number here. And so that's deeper and deeper and deeper, but it's turning around. So the data is showing that it's sort of starting around helium, trying to get to proton, and then changing mind and going towards silicon and maybe eventually iron. The fluctuations is also consistent with that, so that there is large fluctuations to begin with, and then it becomes less and less fluctuating as we go to higher energy. So it seems to be changing in towards the silicon in terms of the composition. Okay, so if you translate that data into a model that explains both the spectrum and the mass distribution, that's what you get. You have protons sort of dominating before the ankle and then dying just before the ankle takes over. And then we have the helium coming up and down. Eventually the silicon, well, the A for 22 to 39, and then the 38 and above put all together here at the end. So what it's showing is that you probably have sources that are accelerating protons and everything else, and probably the maximum energy is for a proton is turning around just at the ankle, which is very surprising. And then, everybody else is following a similar trend to turn around, given that accelerators tend to be proportional to the Z, the charge of the particle, and not the A, right? So anyway, that's the best explanation for the data, but it is a bit confusing. But let me go back to what I was bringing up before, which is there's also another effect that happens at these highest energies, and that's called the Gzk effect. And the Gzk effect, let me jump here, is the effect that happens to all of the different nuclei. But let's just take protons for an example, which is a proton at 10 to the 20 electron volts sees the microwave background as a gamma ray emission. So it is very destructive to a proton, which means that it will interact, make pions, and that pion production will lower the energy of the remaining proton, the leftover proton or neutron that then becomes a proton, and create lots of pions. And those pions then will create lots of gamma rays and neutrinos. The gamma rays will also interact with the microwave background, so they might not show up very fast, but the neutrinos will. And that's why neutrinos are such wonderful ways to understand the cosmic ray story too. So if you are able to detect these neutrinos, you're able to talk about not only the source, where it's coming from, but also how it's propagating from the source to us. So I'm assuming everybody is well versed on neutrinos. So here's, as you know, the standard model of elementary particles. We have the quarks, the leptons, and the gauge bosons, and the scalar boson. And the neutrinos are, a favorite messenger for astroparticle physicists, and we still need to do more to understand them at the highest energies. Here is just a summary, an older summary of the types of fluxes that you expect for neutrinos. There is a cosmological background of neutrinos similar to the microwave background, and that's a very tough thing to detect, but maybe we get there. There's the solar emission, there's supernova burst, and these are very important for interact in the atmosphere, the same that make all these showers, and then they translate some of that energy into creating neutrinos, and those we can observe. And then eventually the flux of atmospheric neutrinos is falling down with the cosmic ray spectrum, and then we get to actually start seeing the astrophysical neutrinos, and the cosmogenic neutrinos are the ones produced by this Gzk effect. By the way, I didn't introduce Gzk. Gzk is Greisen, Zeppelin, and Kuzmin. And the three of them in the 60s, when the microwave background was proposed, they already predicted that there would be an interesting feature, if not a termination wall due to the pion production for protons. And this is shown here, the interaction length and the energy loss length for protons around 10 to the 19, 10 to the 20. So Greisen in the US and Zeppelin and Kuzmin in the Soviet Union proposed it in 66, just after the microwave background got discovered. And Berezinski and Zeppelin were the ones to talk about these cosmogenic neutrinos, the neutrinos produced by this effect that we can in principle observe. All right, so how are we doing in observations? We've done well with the solar and the supernova burst, which was unplanned, but very nicely a great finding. And then we're now, and these are all Nobel Prizes, and then we got Nobel Prizes to Art McDonald and Takaaki Kajita also for using the solar and the atmospheric neutrinos to show the neutrino oscillation. So one beautiful image from Super K is the sun in neutrinos shown here. So now we are in the phase of this astrophysical neutrinos being studied, and IceCube is leading that. IceCube is a detector of a kilometer cube of instrumented ice around the South Pole. Basically, they dig holes and put photomultiplier tube strings and very deep ice. So the holes are almost 3 kilometers deep into the bedrock, and then they instrument this piece further down where they can basically observe light coming from production of particles. Say a cosmic ray can do it, coming down and then making particles cross it, or a neutrino, for example, from coming through making a muon, and an upward going muon is a very clear signature of a neutrino. So here is one beautiful famous event from IceCube that correlates with Texas 0506 a blazar observed also by the gamma ray telescope. So you have MAGIC, Fermi around that emission, and previous observations from other electromagnetic sources, observatories, and it seems to have a neutrino correlating. So that's the beginning of doing astrophysics with neutrinos at the highest energies, and these are 300 TeV that we're talking about. And then eventually the cosmogenic is what we would like to see too. The problem is that with the composition of Auger, the cosmogenic neutrino flux went down quite a bit, and it's going to be tough to observe. So here's a sort of summary of the gamma ray emission that is being observed. So all the detections of Fermi, for example, and the cosmogenic photon flux. So Fermi plus the the possibility of seeing it at higher energies are starting to reach down to the cosmogenic photons produced by those interactions. And then we have the neutrinos. And again, there's a lot of uncertainty given the models. And here's where IceCube is starting to detect these astrophysical neutrinos. Okay, good. I'm running out of time, so I'm going to just skip just mention one more interesting event, which is the gravitational wave neutron star merger, which will be one of the brilliant sources for us to detect. And unfortunately, no neutrinos were observed, but both Auger and IceCube were would be able to see something if they were in the right position. Auger for sure actually has an overlap with the window of observation of that event. But we haven't seen neutrinos with gravitational waves yet. So in terms of multi-messengers, we've done electromagnetic spectrum with gravitational waves and electromagnetic spectrum with neutrinos, but not neutrinos with gravitational waves yet. And this is what we would like to do in the future. So back to my questions, right? So these are the two questions that we're trying to answer. I hope it's clear that measuring better the spectrum composition and anisotropies at very high energies and studying 10 PeV neutrinos will be very important to understanding everything. And here we go. So POEMA is the probe of extreme multi-messenger astrophysics, and we designed it to study ultra-high energy cosmic rays and the cosmic neutrinos at the higher energies compared to the astrophysical neutrinos that IceCube is seeing. We have a large collaboration, 70 scientists that participate in designing this from 32 institutions in 13 countries, many members of previous collaborations, and the leading institution is us at Chicago. The kind of design is to do two types of observations: looking down for ultra-high energy cosmic ray emission, looking down from space, but seeing also downward going showers, the traditional way that Auger does it. But we would have, an array that for the Brazilians on the call would be, of the order of Belo Horizonte, São Paulo, and Rio. So some, scale of trying to instrument this whole area. As we turn these observatories, and we want to, because we want to have stereo vision for doing a precise measurement of the maximum of the shower. So that's important to do composition. If we turn those two telescopes towards the limb of the Earth, then we obviously get a much larger atmosphere to look at ultra-energy cosmic rays coming down. But then we also start observing the tau neutrinos upward going showers towards our telescope. And this would be about 15 degrees below, a range between 0 and minus 15 degrees from the limb of the Earth. Here's the engineers and some of our team at NASA doing this study. I'm going to quickly just show you pictures of what we designed. So we have a mirror, a camera, and a beautiful correction plate. We would be pointing these things down. We want two of them so they get compactified for launch. And the camera is one of my favorites because we have two types of instrumentation. One to look at the fluorescence, which is a microsecond scale camera, which we have built for Ayuso. And then we have the Cherenkov camera, which we are now building for Ayuso SPB2 to look for the neutrino Cherenkov signal, which is tens of nanoseconds. So, we have a much faster camera that we're now building on Ayuso SPB2. The idea there is that we will have a lot more exposure as a function of, this is declination compared to what Auger and the telescope array can do on the ground. Obviously, the higher the energy, the easier for us to see because we can point all the way to the limb. And then we should be able to start seeing where the hotspots with starburst galaxies, for example, are located. The other thing we do is to look for these tau showers coming upwards, and that tells us about neutrinos above 20 PeV. And for that, we have a very long list of different possible multi-messenger producing sources. And, neutron star coalitions are one of the best there. So that's what we're aiming this project towards. Here is just a comparison of the coverage of the sky between IceCube, which is, stuck in the South Pole. So as the Earth turns around, it doesn't see a lot of the sky. While POEMA, which is flying, it can see the whole sky. It can see all the dark sky at a given position of the Earth. And as the Earth moves around the sun, it sees the whole sky. So that's the great thing about, one of the great things about being in space. One is a very large volume, so low fluxes are easier to detect, and the others that we can see the whole sky as the telescope rotates around. So here's a little cartoon of what Poema would be observing towards the limb to see the sources on the other side of the Earth. And now I wanted just to give you a sense of what we've been doing because we're running out of time. So Poema is something for the future, which we hope to build by the end of the decade or in the beginning of the next decade. In the meantime, we've been doing a lot of different prototypes, and one of them is right now with this cosmonaut in the International Space Station. These are all different telescopes that we are doing as part of one large collaboration called the GEMUSO program, the Joint Experiment Missions for the Extreme Universe Space Observatory. We have USO telescope array, which is on the ground. We had one balloon flight in 2014. We had the first super pressure balloon flight in 2017. Mini USO is now operating on the space station. We are launching SPB2 in 2023. We are planning with our Russian colleagues the 2024 deployment of a K-USO, and then eventually at the end of the decade, beginning of the next, Poema would be our hope to be built and launched. So here's our first flight overnight in 2014. And what you can see with our camera, which is this microsecond camera for fluorescence, is what a shower would look like. This is what a shower would look like. And that is done actually through a laser shot by a graduate student on a helicopter at night under the balloon. So that was pretty exciting. That graduate student is now a postdoc here with us in Chicago, but he had fun trying to shoot the laser in the right direction so we could see from the balloon. That was the first test flight. Here's the first flight from a super pressure balloon in New Zealand. And this is our team putting things together there in New Zealand, and included graduate students, undergraduates, postdocs, and more senior scientists. The design was a refractor with one of these very fast cameras with the microsecond time scales. And here's the launch in April. Unfortunately, we didn't fly as long as we wanted. Once these things are launched, they become as large as a football field, or a soccer field. The size of this helium balloon is, of a soccer field scale, and it's super pressurized, so it becomes buoyant in the atmosphere, and it stays at about 33 kilometers altitude. The reason we use New Zealand is because that's a perfect place to start rotating around Antarctica and stay mostly on the ocean, so we don't go over cities and we don't go over countries that we need permission for, and it gets complicated. So we can sit there and rotate around for as long as the balloon will have us do it, which in the case of the super pressure balloon, the goal is to reach 100 days. The winds are very stable in some times of the year, not always, but at the altitude we're talking about, our flow above 30 kilometers or so, they are fast at 100 kilometers per hour and very stable. Unfortunately, we had a leak in our balloon, so on day 3 we started going down, and we had ballast, so we came up again, and so we went up and down until we couldn't do up and down anymore, and we ended in a short flight in the Easter Island region. So we didn't do what was planned. So we're hoping for, so this was 2017. Previous super pressure balloon flights happened to have 46 days and 32 days. So in principle, we should be able to get I already mentioned our cosmonaut, and so I'm skipping showing him again. Here is what we're building now. So this is USO SPB2. It has 2 telescopes, the Cherenkov telescope towards the limb of the Earth and the fluorescence telescope pointing down. We are, large collaboration again, 13 countries involved. Cameras are being assembled now, both for the 2 types of telescopes. One camera is the microsecond time scale. The other is the 10 nanosecond time scale, the Cherenkov camera, which is very new. We will take the Cherenkov camera in the field to do field tests by the end of the year. And early next year, we should do field tests with the fluorescence camera, and then ship everything to New Zealand by the end of next year to fly in 2023. So crazy times, but it should be fun to get there. We are pretty busy right now. So let me summarize and take a breather and questions. So Poema and USO SPB2 Oh, and this is in Portuguese. Sorry about that. I thought I caught all my Portuguese slides, but here's one of them. So I'll translate to English. So Poema and USPB2 are designed to open new perceptions of the universe or new windows of the universe, to discover the origin of ultra-high energy cosmic rays, to observe neutrinos from extreme events in the universe, and to study astrophysics and particle physics of unknown sources or known sources, but better. We have the Poema design ready to be started in the NASA process, depending on prioritization, because the Poema type of payload is quite expensive. And we have the USPB2 being built right now, also NASA supported. The super pressure balloon is a NASA payload. And so that's what we are working on right now. And we hope that this first flight with the Cherenkov camera will actually give us results of not necessarily the neutrinos from a target of opportunity source. We won't have, maybe we would have to be very lucky to see a neutrino in terms of timing and exposure, but we should be able to see cosmic rays just above the limb, which have also Cherenkov emission. And that's what's going to be our science goal with that camera. And the other one would be for the fluorescence that we know is there. We have seen that before. So here is to let you breathe, let me breathe and see a little bit of the launch. I'm going to turn off the sound. So this is the launch of USPB1 in 2017. The balloon has the right amount of helium to stay afloat at 33 kilometers. And after launch, it should lose that little neck holding thing there. There is in red below a parachute. So the balloon actually ends where the parachute begins. The parachute is to be able to bring the payload, which is what we name the telescope in balloon terms. And this is the lucky guy that needs to unplug our telescope just in time as soon as the balloon crosses over. You can't wait too long, otherwise it drags the crane. And if you do it too early, it hits the crane. So it has to be just right. And so he's very happy, as you can see. Yeah. So there goes USPB1 flying up from the southern island of New Zealand in Wanaka, around Wanaka. And then later you will see the balloon inflated at flight altitude, which is a much bigger guy right there. And below it is the parachute. Once the mission ends, if hopefully we can choose to end it above land, then we would bring the parachute down and be able to see, to recover the rest of the data that we didn't download. Okay, questions?
Okay, thanks a lot, Angela. It's really interesting. So I think now we can open for questions. I have two, maybe I can start. So in one of the first graphs you mentioned, that is this cosmic ray spectrum. It was a huge range of, but there was a line below all the points. What was the line? It is one. I don't know. Yeah, this one. The line is because.
Oh, energy? No, which? Oh, this line is a power law e to the minus. Yeah, this is just what an e to the minus 2.7 line would look like.
Ah, okay.
But up to here, and then the turnaround, obviously. So this is just a to guide the eye what an e to the minus 2.7 looks like.
But then when you move the line, it's okay.
It's just to guide the eye, so it's still there.
Okay.
But then, when we plot it with multiplying by 2.7, if we were going all the way, let me explain that because I didn't introduce it right. So here we're starting at 10 to the 9 electron volts, which the electron volt got cut off. Apologies for that. So 10 to the 9 to 10 to the 20, right? So then you can see that, it works okay. And then it gets a little bit above, and then it gets a little bit below, and then it gets above again, right? But and here it turns around. So it's not e to the minus 2.7. But then we're going to zoom in at 10 to the 13 and not start at 10 to the 9. So 10 to the 2.7 is not the best fit for the whole spectrum, but it is a good fit here up to the knee. So, this is multiplying by times 2.7. So erasing that, going down. And here is also a 14% energy range that I didn't highlight. And then when we move to this spectrum, we're doing EQ. So, compared to that one, this is not following anymore. This is now a flatter version of that part, right? So this becomes flat. Hopefully that was clear.
Okay, okay. And the second question is just maybe I miss that is the second need that is new or it's some controversial. Maybe I misunderstood this.
Yeah, I think that it is new, and in the sense that it's not this year's novelty. It's been around. It's been a tentative, argued upon measurement for a little bit of time. But now I think in the community, everybody's convinced it's there. And one of the challenges was to actually be able to measure with the same detector many orders of magnitude. Because when you're piling up different detectors and trying to solve the data together, the systematics comes in, right? So if we go back here, you see that there's many different detectors. So for example, if you didn't measure with Auger these low energies, you would have to guess what happens with the black as it moves towards the knee, right? But this is one reason why one of the improvements or upgrades of Auger was to put more dense arrays to be able to extend the energy range to lower with the same instrument. Because the energy systematics goes 14% energy systematics goes in this directions, which is what explains the telescope array greenish points being different from the Auger points here in black. So this is the direction that you would move the dots. And then if you want to connect to, for example, Cascade, which is sort of in the middle here, but Cascade again, it's a couple of orders of magnitude. Then you have at lower energies, Hawk, Ice Top, sorry. And again, there are systematics between these points, so it's hard within any given energy range to be able to explain the whole story, right? So when this knee started showing up, and I could be wrong, but I think Cascade was one of the first to see this. People didn't believe it, and now that we have lots of experiments extending those lower energy ones to higher energies and higher energy ones to lower energies, it became pretty clear that there is another bump there. And Auger is one of the easiest places to see it, even though with the systematics there is some you could imagine some systematic that is highly energy dependent that erases that, but it's very hard to do. So I think there is a second E. But if your question was, okay, maybe there is a second E, why is there a second E? That's a harder question to answer. And here is one way to look at that question, which is somehow we probably need more than one source to explain the plotted in 2019. There was another possibility of a bump here. That's not what we see in Auger. So every year the bumps move around. So the theories get more and more challenged. So if you look at there, there is no second bump there. So anyway, so now the bump is further closer to the ankle in that sense. So just looking at a little piece is not enough, which is why we want to focus at the highest energy so we can actually point. And that would really help. And also try to, we need a lot of statistics to be able to separate the different flavors, which is what Auger is doing at these energies.
Thanks. So that is Dimitri, please, Dimitri, go on.
So maybe I'll first let Lucas to ask his question because I'm the organizer, so
okay.
priority.
Okay, so Lucas, please.
Okay, thank you. So, Professor Angela, I would like to ask about the perspectives of the application of everything you said today on the detection of gravitons. If you have anything about that to comment.
Zero comment there. Our guys, where is it here? Yeah, so, the best one can do at this point is, the radio wave analogy to photons in the gravitational wave business, right? So this LIGO measurement is hard enough to get to detect. So I don't have much of an idea how we can detect gravitons, but we certainly can detect gravitational waves, and that's really brilliant. And then we're moving in even longer and longer wavelengths, so it's not close to a quantum possibility there.
Okay, thank you.
So, Dimitri?
Thank you, Angela, for your very nice talk. Maybe first I would like to ask about this exponent in the spectrum 2.7. Is it somehow theoretically explained, or that purely phenomenological result?
The 2.7? Okay, so that is the best explanation is shock acceleration, Fermi shock acceleration. And it does give you around that energy dependence. So it's not that hard to get that kind of a power law. So we don't worry too much about that. I mean, there are models there, shock acceleration in supernova remnants. That area is getting much better in terms of predictions from first principles in the simulation. So folks are now able to simulate the supernova shock plus the effects of the cosmic rays themselves, sort of the feedback of the cosmic rays on the shocks and the magnetic field. So it's becoming very well studied, I think. So it's very exciting in that sense. And I think that is not a challenging power law to get. However, I'm going to take your clue here and say, however, this guy here are very steep power laws. So, so this is in cube, right? So these things are, say, take the green line. So if we look, the problem with the spectrum at the highest energies that we're, adding most energies, but especially at the highest energies, is that we're adding lots of flavors and lots of, different variations. So that the Z is making, or the A is making a change. And so knowing what is the accelerator that is trying to accelerate these things, injecting into extragalactic space is not so trivial. But if you take a look at the shapes that either the gray or the green, you see something that is coming down and then some new source coming in, right? And this new source is very hard, meaning that it gets a power of either the -1 minus, it's stronger than shock acceleration by quite a bit. And that is not super trivial to do. So, there's a lot of interest, and we worked on this. For example, one of our favorite models was to have newborn pulsars. So pulsars that are rotating really fast, and with their magnetic field, they're able to accelerate to a power law, which is E⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ maybe these are also neutron star coalescences. They can make also the sort of very fast spinning neutron star, which then becomes a black hole when it cools down. So, it could be a transient way of getting something hard like this. But, for a 2.7, shock acceleration is fine. I mean, people will argue over from the source. So it's what we observe on Earth is both the injection plus the transport from the source to us. And in the low energy cosmic rays, the transportation has to do, the propagation from source to us has to do with the structure of the magnetic field of the galaxy, how much they rotate around, how much they escape the galaxy. So it's a combination of many things that multiply the injection spectrum, which is e to the -2, e to the -2.5 on the shock acceleration side. So 2.7 is not hard to explain, but this thing here is a bit hard.
Okay, so my next question is about actually this Voyager spectrum, and this looks a bit model dependent to me, at least from a naive point of view. And do you think that something exact can be extracted, and do you think that there's any place for new physics here in this plot?
Yeah, so let me see if I find a better plot. One big worry, let me use this guy here. It's an old plot, so I put it in the back, but this is the model dependence is shown in the lines, right? So the data itself is quite, I mean, with high statistics, except for the 14% energy error bars, we are starting to get very good measurements in the Auger telescope array side. The challenge is the interpretation, right? So to interpret these things as either proton, say this guy is a proton and this guy is somewhere in the middle, is not so easy. And the reason is we don't even have sort of say for interactions, right? So we have different, so here's older versions, so QSJet, 3 types, SIBO, QGES-JET, and EPOS back in the past. Now, I'm not super sure I put the models in the current figure. Maybe I did, maybe I didn't. Not really. So I will put, but you know, these lines here, these red lines is one model. It's apples, right? And so there should be many lines per element, depending on what you assume the forward direction of production. So what has been happening is a lot of interaction with the LHC folks looking into the forward direction to be able to fit the same model. So apples, for example, is an LHC fit model. So its extrapolation is not so bad compared to others that don't do that. So measuring the low energy stuff well in the forward direction helps figure this one out.
Okay, thank you very much.
Okay, there are 2 questions on the chat. There is one by Peter. I don't know if it's a long one. I don't know if I understand everything. It's basically about gravitational waves, if it's possible to detect or how it influences. I don't know if I follow the question.
Yeah, so I mean, what I mentioned before is gravitational waves and neutrinos will be a really nice thing to detect, right? So these guys and the neutrinos will be coming at the same time from the same source. So for example, let me take one of those models, just so you can see where we can reach those guys. Where is it? There we go. Okay, so here is a plot I didn't show, but another one. So here is predictions for transient neutrino production of different emissions. One is, you know, a soft gamma ray repeater, and the other is a neutron star coalescence. So the neutron star coalescence model of Feng and Metzger is really fun for us because it peaks right where Poema gets the sensitivity to go deeper into the plot. So this is the flux at, you know, weeks to a month later. There is a delay because if you remember what we're talking about is 2 neutron stars. Whoops, where are they? Here. So it's this little video. Well, let me go this way. That might start the video. Hello. Yeah, so 2 neutron stars are coalescing, generating gravitational waves. And then, you know, usually they will become a black hole if they don't lose any mass, because they usually 2 masses of neutron stars are higher than another neutron star, but they can live for a while and they make a very high density, hot, you know, baryonic matter, nuclear density, higher than nuclear density materials, which also produce neutrinos. And, you know, depending on the whole, you know, emission transport of neutrinos, eventually you get the neutrino flux out. So that would be a brilliant measurement to get a gravitational wave followed by neutrinos later. Black hole coalescence, for example, unless there is a lot of material around, in principle, no neutrinos are emitted. But if you do have material around and with the black holes, then you could produce some neutrinos. The other source that we would love to see, which IceCube is starting to have hints of also, is the tidal disruption events. Those are when a star comes very near a black hole and that gets disrupted, and that disruption can also produce neutrinos. So those are some of the, you know, favorite models for us to do, you know, our neutrino at the same time as gravitational waves or the binary coalescence.
You mentioned that you you already tried. I mean, the Auger already tried to see gravitation. Well, neutrinos from gravitational wave event and you didn't see anything. So if you never observe anything, what would this mean?
Yeah, that's the Auger limit here on that, a neutron star coalescence. IceCube also did not reach it. So what you can conclude is that this model is viable, right? Obviously, the theorists put the model so that it would not produce more than Auger and IceCube didn't see. But so there are 2 points to be made. One is that the flux is at the level that you need something bigger to see it. So we are proposing Poema. Another team is proposing, with a little overlap, Grant, which is a very, very large array of radio antenna in China, and they're starting to build a prototype. And then there is the proposal to do IceCube Generation 2, which is a much larger South Pole based observatory with radio arrays going to a much bigger distance, again, to see increase by quite some. It won't be a kilometer cube anymore. It will be many, many, many kilometers cube. So those are proposals that are being debated right now, what to fund when. And then, in principle, all those proposals would be able to see the neutrino emission. But the ones that we have on TARIS, Auger, and IceCube did not see it. The one thing, though, is that, what I mentioned before is the coverage of the sky, right? So Poema, the nice thing is we can see the whole sky. IceCube can see well a piece of the sky at these energies. At lower energies, neutrinos cross from the whole Earth, so they can see lower energy neutrinos through the whole sky. But when you get to the high energy ones, they don't, which is why we point at the limb at PeV energies, at tens of PeV energies. So here is the actual plot of the region where the gravitational wave happened, and Auger didn't see it and could have seen it, which is why this limit is important, this Auger limit here. And this is for a fast burst, and this is for a longer burst of neutrinos. And then IceCube is, let's see, here with the green. So this is down going and this is up going. It wouldn't be, well, if you were looking at high energies, it would have to be down going or most of the time. So, that would be a possibility. And they did see a few neutrinos. They always see some events. They are not sure if they're neutrinos or not, but not coincident with the gravitational wave, which is how you get that limit in black.
I think there is one more question on the chat. It's by Gilberto. Do you can look for a specific source in the space?
Right. So that's exactly how. So if we are here, right? So this is our orbit. And what we are seeing is you're looking at the limb of the Earth, and at 525 kilometer altitude, and that the limb is at 66 degrees. That's correct, Angela, right? Around there, from zenith. So it's if you're on the Earth, then the limb is pretty close to 90 degrees there, and then you go a little bit lower, right? So everybody who, say you have a source which is in the direction of the limb, but any 360 degrees around that limb. So we actually have the possibility of seeing a circle that is moving with the telescope. When the telescope is on the other side of this Earth, it is sunny, so we don't see an observation. While when it is on this side, it is dark, so we can see the neutrinos coming from. So what we can have access is half of the sky as we, if we can rotate it and point it in any direction. The time to repoint depends, but it could be minutes, it could be seconds or minutes. So if we get if somebody sees a gravitational wave, we get an alert that might take a minute or so, we can repoint, take a couple of minutes, so then we would point, right? So if it is a very fast burst, like the one on the right-hand side here, prompt emission, first the prompt emission is not very good, but this is less than 10 to the 5 seconds. And so you would need, to be a bit lucky to be pointing in the right direction. For the neutron star, this is the gamma ray burst. For the neutron star coalescence, the idea is that the flux actually goes higher at about 10 to the 5 to 10 to the 6 seconds. So that's perfect for us. So the neutron star coalescence would be our primary targets, but we would obviously look at anything interesting in the sky and see if we see a neutrino. At the energies we're in, and it's much higher than the atmospheric production of neutrinos, because we're at tens of PeVs and above. So that is a nice thing. We don't have to worry about the atmospheric neutrinos, which IceCube at the lower energies has to.
Okay, so I think maybe the one more by Fernando Henrique. Fernando Henrique, maybe.
Okay. Okay, thank you. Do you have any? Do you know if there is any reason for the Pierre Auger Observatory is located at Argentina, or there is no another reason for that?
Yeah, I think, well, there was a committee. So the idea of doing something in 3,000 square kilometers is, makes it very difficult to find such places. There is a requirement on the altitude. You don't want to make it, at the sea level, because you want, given the energy of the showers you want to see, you want to be close enough to the maximum of the shower, but you don't want the maximum of the shower to be below your altitude either, right? So you don't want to be too high that you don't see the maximum of the shower. So these things, it's nice to have little hills around so we can put telescopes on top of the hills. So, when you ask all that, and then you ask what country / collaboration or group in the collaboration is able to give support in the infrastructure, right? Because we need people there, we need a site, we need a building, we need engineers, we need technical folks. So it's not a high intensity maintenance type of thing. It's very self-sufficient the way it was designed, but we do need some, infrastructure. So Argentina was the best if you put all these other categories, and the Pampas Amarillas around the Mendoza area is where it's located. And if you happen to be
Thanks a lot again, Angela, and hope to see you in person here in Natal. And thanks everybody for the participation, and see you next week. Bye.
Thank you so much. Pleasure to be here. Bye-bye.
Thank you.
Bye. Thank you.
Bye-bye.